In this part of the course, we are going to talk about enzyme kinetics. In other words, how to quantitatively describe enzyme catalyzed reactions. And this is not much different from just any chemical reaction. And the first in the list, I would like to cover the term reaction molecularity. This term is applied for elementary reactions, reactions that undergo through a single transition stage. And you remember that some of the reactions are more complex and they have several transition states, intermediates, and so on. So terms reaction molecularity is not applied for non-elementary reactions. So now all elementary reactions can be divided to unimolecular, bimolecular, or thermomolecular reactions. In unimolecular reactions, a single reactant participates and produces one or several products. In bimolecular reactions, there is a need for collision of two particles, and they produce several products, one or several products. In thermomolecular reactions, three particles participate, collide, and produce one or several products. So I don't have an example of thermomolecular reaction on this slide because they are quite rare. So basically in biochemistry, we mostly focus on unimolecular and bimolecular reactions. There are no molecularity higher orders because there is just simply no significant chance for more than three particles to collide at once. So any chemical reaction is described by its rate or velocity, indicated by letter V, which is a change of the product over time, or negative change of reactants over time. This negative stands for reducing the concentration of reactant over time, and the positive sign here stands for increasing the concentration of product over time. And by definition, it is proportional to the concentration of reactant. And we can write similar equation for bimolecular reaction, in which rate of the reaction will be proportional to the concentration of both reactants, reactant A and B, with a proportionality coefficient K. So now for complex reactions, non-elementary reactions that undergo several stages, we cannot apply term molecularity. We need to apply term order of reaction. The order of reaction is defined as the power to which the concentration term for each reactant has to be raised in the equation. So if molecularity must be an integer number, 1, 2, or 3, the order of reaction can be a non-integer number. So in other words, this power can be 1.5 and so on. The rate of reaction is mole per liter per unit of time. It's either second or minute. In biochemistry, minutes are used most frequently. And it is applied, this unit is common for rates of unimolecular or bimolecular reactions. However, in order for the unit to be the same, the constants of unimolecular and bimolecular reactions has to have different units. The unit of unimolecular reaction is inverse seconds or minutes, while the unit of bimolecular reactions is inverse mole per liter, inverse seconds. And I have to say that this is important for the future when we go back to calculations, to enzymatic reactions. Please remember these units. For elementary reaction, their order and molecularity are numerically the same. Now let's take a look at reaction of first order. From now on, I'm going to use term order, assuming that this reaction is not necessarily an elementary reaction. So as we know, the rate of reaction is proportional to the concentration, and let's transform and solve this differential equation. So I transfer all parameters containing concentration of A on the left and time on the right integrated from time 0 to current time t, and my concentration at time 0 and concentration at current time. And when I take antiderivative of this expression, I will get a natural logarithm of A minus natural logarithm of concentration of A at initial time point. And then it can be rewritten this way, and I unlock this both parts, and I get my concentration of A will depend on the initial concentration of A, and it will decay exponentially. So here on the slide you see a graphical representation of this equation. The concentration of A varies with time. It reduces reduces with time, and concentration of P increases with the time. Now, an important characteristic of first order reaction is a half-life time. Half-life time is the time required for 50% of A to be decomposed. It can be found like as natural logarithm of 2 by K. So it's actually doesn't depend on the concentration, on initial concentration of A, which is very interesting. But it depends on the kinetic constant. This equation, this half-life time, is widely applied, for example, for radioactive decay. Other assumptions that are important in practice, but we didn't discuss yet, are that there are no inhibition of the enzymes by the products. So no binding of the product to the enzyme, which is not true in many cases where product inhibits the enzyme. It's so-called feedback inhibition. No enzyme inactivation. So enzymes are obviously sensitive to environmental factors and can be easily inactivated. In practice, enzyme efficiency is often characterized by the parameter kcat by km, which includes the new parameter kcat, but assume that kcat is same as k2 for a simple reaction, but in general kcat is a measured catalytic rate of the reaction. The higher the kcat to km, the more efficient the enzyme. I would like to take your attention to two enzymes in this table. Catalase. It has a relatively high km and high kcat, and the efficiency of this enzyme is high. It's above 10 to the 8 inverse mole by inverse seconds. And fumarase, it has much lower km and much lower kcat, but the efficiency of fumarase is almost same as for catalase. It's also very high, above 10 to the 8. This indicates that you can achieve high catalytic efficiency both by reducing the km or by increasing by kcat. Next time we are going to talk about enzyme inhibition. We can also solve a differential equation for a bimolecular reaction in which two reactants are identical. A plus A equals products. The rate of this reaction can be written as a negative change in concentration of A over time, and also it's proportional to the concentration of both reactants, A by A, with a constant K, right? So let's, when we solve this differential equation, this part, we will get this expression right here, and half-life time for A in this case does depend on the initial concentration of A. So let's talk about enzyme kinetics. Why do we need to study enzyme kinetics? First of all, can give us an insights in understanding how enzymes work, which amino acids are important, and reveal some details of catalytic mechanism of the enzymes. It also helps to predict how enzymes behave in living organisms, and which has some medically relevant significance. And of course, in drug development, enzyme inhibitors are used for inhibition of enzymes. And of course, we need to know how much an enzyme is inhibited by this or that drug. Enzyme kinetics is very often quite complex and hard to describe, especially in living organisms. However, in order to get some quantitative estimations, we can use a simplified enzymatic reaction scheme: enzyme plus substrate, and this is a reversible first reaction, forms enzyme substrate complex and produces product P and releases the enzyme E. So now the second part is not reversible, and this is a simplification. Let's attempt to solve this equation. So again, this is Michaelis-Menten scheme that we need to remember, and we are interested in product accumulation. That's why we write the rate of the reaction, in other words, change of product over time, equals a kinetic constant K2 by the reactant ES, because product is only produced from ES. The change of ES over time is going to be equal to this expression, and this expression has three terms, and each term stands for a reaction in which ES participates. ES is accumulated due to one reaction that with a constant K1, so it's produced in this reaction, and it is decomposed in two reactions which are characterized by constant K-1 and K2. So now this first term is responsible for the accumulation, concentration of E by concentration of S and by K1, so it comes with a plus. And the other terms that are responsible for decomposition of ES, they contribute with the minuses, because obviously the concentration of ES will be reduced due to these reactions characterized by K-1 and K2. Okay. Now, what else do we know? It's very easy to measure total concentration of the enzyme, and it now equals to the sum of all forms in which enzyme participates. And we have only free enzyme, and enzyme as a part of enzyme substrate complex. Substrate, we also know the total concentration of substrate. And now where do we find the substrate? The substrate exists as a free substrate in solution, as enzyme substrate complex, or some of the substrate is already converted to the product. Let's take a look at the system of differential equations and decide if we can solve them in general or not. To solve any system of equations, the number of equations is supposed to be at least equal to the number of unknown values. We have 4 equations, and let's take a look at the unknown values. How many of them do we have? So first of all, we do assume that we know K1, K-1, and K2. These are characteristics of each enzyme, and we assume that we know which enzyme will work, and we know these characteristics. Second thing is that the total enzyme concentration and total substrate concentrations are often easily measurable, and we also assume that we know these parameters. However, we don't know any other parameters, which are rate of the product accumulation and rate of the enzyme substrate accumulation, enzyme substrate complex accumulation. We don't know the enzyme substrate concentration, enzyme concentration, or substrate concentration, or product concentration. So altogether, we have 6 unknown values. So the system of equations cannot be solved. And that's why, in order to solve it, we need to take some assumptions. Historically, this system of equation was solved under assumptions of equilibrium, in which we assume that the reaction of enzyme substrate decomposition is much faster than actual catalytic reaction, and the equilibrium between enzyme substrate can be established much faster than the conversion of enzyme substrate complex to the product. However, this assumption is not always applied, and it's not actually needed to solve the system, and that's why we skip and move to our first assumption that we use, assumption of steady state. In this assumption, we state the concentration of ES does not change, it is constant. And if it doesn't change over time, then this expression equals 0. Is it true for a biochemical reaction? So it is, in some cases, an acceptable assumption. Let's take a look at the change in concentrations of participants in a typical biochemical reaction. Obviously, substrate concentration goes down over time, product concentration increases. And if you take the concentration of enzyme substrate complex, it increases at the initial very fast time, and then it remains more or less stable. So if you assume that change in ES equals 0, this helps us to get rid of one unknown values. So we have 4 equations and 5 unknown values only. Now, another important outcome of this assumption is that the rate that we are looking for, the rate of the product accumulation, is constant. It's time independent. Indeed, if ES is time independent, K2 is constant, then the overall expression is time independent. Second assumption is the assumption of initial rate, which helps us to get rid of the product concentration. Consider our reaction at the very initial time point, roughly right here. At this time point, the product concentration is still small in comparison with substrate, and that helps us to neglect the concentration of the product in comparison with the concentration of the substrate. However, in this case, we change our velocity to V naught, which stays for initial velocity rate. Now we can take a look how the system of equation changes. So we replace V with initial velocity rate and we scratch the product. Now we have 4 equations and 4 unknown values. In general, we can solve this system of equation. However, in order to further simplify it, we can take another assumption. And this assumption is that substrate equals to initial substrate concentration. This is true only if the initial substrate concentration is much greater than the initial enzyme concentration, so at least 10 times greater. In this case, only a small fraction of substrate will be bound to the enzyme, no matter what is the affinity of enzyme to substrate, and we can neglect this term in the equation, stating that substrate concentration equal initial substrate concentration. So our last equation changes. So pretty much the substrate concentration right here can be substituted with initial substrate concentration. And overall, I have rewritten here the system of already 3 equations, and our substrate concentration is initial substrate concentration. And now we can solve this system. So what I do next, I find enzyme concentration from equation number 3 and plug this enzyme concentration, replace this enzyme concentration with the expression, and solve this equation for ES and plug ES into this equation. So again, enzyme concentration equals enzyme total minus ES. So I replace my enzyme and find ES concentration, rearrange it, and plug this ES concentration in the first equation. So, and get this expression. Let's take a look at this expression, which is called Michaelis-Menten equation. This is the rate of enzymatic reaction depending on all known parameters. Initial substrate concentration, total enzyme concentration, and the kinetic parameters. This expression right here is called Michaelis-Menten constant, and K2 by ET is called Vmax. We will discuss what this is. Let us first talk about a little bit about Km and its physical meaning. First of all, I would like to draw your attention towards units. K-1 and K2 are constants of first order reaction, and they have same units of inverse time, inverse seconds, for example, and they can be added, right? So hopefully this will help you to remember that K2, it can be added to K-1, but K1 cannot be added to K2 or K-1. And in denominator we have the constant of second order reaction, and the unit for Km equals mole per liter. So this is the unit of concentration. This is very useful and important to remember. Now Km often can be used as a characteristic of enzyme substrate interaction. If you rewrite Km in this expression, K-1 by K1 plus K2 by K1, so this is just rewritten, and in some cases K2 is much lower than K-1, and you can neglect this term in the equation, and your K-1 by K1 is just the dissociation complex, a dissociation constant of enzyme substrate complex. So meaning that the lower the Km, the higher the affinity of the substrate to the enzyme. You need to remember the Michaelis-Menten scheme, kinetic scheme, and Michaelis-Menten equation. And we can measure the initial rate of enzymatic reaction on substrate concentration. So this is the rate of the reaction. This is a substrate concentration measured in Km units. This will look like a rectangular hyperbola that is approaching Vmax, maximum possible rate of the reaction, but never reaches it. The important characteristics of any enzymatic reactions that follows the Michaelis-Menten equation are Vmax and Km. The higher the Vmax, the more efficient the reaction. The higher the Km, the less efficient the reaction. On this graph, you can see that Km corresponds to the substrate concentration when the reaction rate reaches half of the maximum available rate.